All right, so today we're going to continue talking about relativity. We'll finish our conversation about relativity today, but so far we've seen relativity affects simultaneous events. It changes times. It changes lengths. We've now seen that it changes velocities. We've seen the transformations. If you want to go from one coordinate system to another, it's not straightforward, right? We have to use those Lorentz transformations instead of the easy Galilean. So yeah, all this stuff matters. But obviously, if velocity now gets affected, then we're going to start seeing other things get affected as well. And we're going to continue that. We're going to talk today. We're going to talk about the Doppler effect. We're going to talk about momentum. We're going to talk about energy and kind of tie all this stuff together. And in fact, today you're going to see the most famous, probably science equation of all time, E equals mc squared. I know you've heard of it. Today you're going to see where it comes from.
I have actually used it once.
Ah, you've used it
Yeah,
in
in
chemistry
chem.
class?
Yeah, in chem.
Looking for how much energy you would get if you like destroyed an electron or something like that.
Yeah, it was something along those lines. It was on an exam.
Yep. All right. Well, today you're going to see where that comes from, right? And I like to joke with Sean about this. I like to tell him that chemistry. I mean, it's just physics without actually doing any of the math or seeing why it happens. And then he's like, "Yeah, that's pretty fair." So, but I know that he definitely is more of a physicist at heart.
He just doesn't want to admit it.
I think so. I think so. That's one of the reasons why I like him, because he's not actually a chemist. Anyway, um, so we're even going to get to that. So you're going to see where that comes from. All right, but let's actually start with the Doppler effect. Now, you guys remember the Doppler effect? Just in general, what does the Doppler effect do?
It changes frequencies, right? Between waves by
Okay.
the position in which they are.
All right, so it definitely has to deal with the frequencies of waves. I don't like saying that it changes the frequency because it doesn't actually change the frequency of a wave, but its apparent frequency changes. So when we talk about the Doppler effect, it's always when we have objects that are moving. Because if two things are stationary, we usually talk about a source, right? And then an observer or receiver or whatever. So if you've got a source and an observer that are both stationary, whatever frequency waves are being sent out are going to appear to the observer with the same frequency, right? So we always have to have something moving, either the source or the person or the observer, right? So one of the places that we actually see this a lot is with sound, right? And this is the old, when a car passes you and you hear the right, or the change of tone in a siren as it goes past you and all that. So we tend to think of it with sound, but it's always about waves. So let me give you kind of just the real brief recap of just plain old Doppler effect and what's going on. So let me pull up my whiteboard here. So imagine that we've got some sort of a source that's sending out waves. Okay, so I'm going to put a little dot here, and this is going to be our source. And then somewhere over here, we've got an observer. And so if they're both stationary, those waves are going to be coming same frequency, hitting that observer, and they're going to sense that the exact same thing is happening. Or let's just go to sound. They're going to hear the same sound that's actually being produced by the source. Okay, but now let's have it so that the source is moving. All right, so let's say that this source starts moving towards the observer. So think about what the net result is going to be. So the source sends out a wave that, let's say, comes out here. And by the time that they're ready to send another wave, okay, this one, let's say, moves out this far. But now the source has moved in. So let's say that they move to this point. So they send out their wave and it's going to be here. And notice that the gap between those has effectively shrunk. So when those finally get to your observer, the observer is going to go, ooh, the wavelength is smaller, or the frequency is greater. And that would mean that they hear a different sound. Okay, so that's what happens if the source is moving towards the observer. Obviously, if they're moving away from the observer, you have the opposite effect. Starts distancing. There's a greater distance between them, because now when they're moving the other way and they start sending out their wavefront, they get further apart. Okay, so that's kind of the deal there. Obviously, if the observer moves and the source is stationary, we see something similar, right? If the source is stationary but the observer is moving towards them, then it's going to appear like the wave fronts are coming closer together. So it's a shorter wavelength or a greater frequency. And then similarly, if they move away, it's going to appear to be greater wavelength, longer wavelength, or smaller frequency. So with motion, we get this to happen. Now, obviously, if we're going to be talking relativity, this is going to matter, because now, I mean, we're moving at super high speeds. And so the question is, what's going to happen here in terms of the apparent wavelengths? So let's just think about what's going to happen. Let's go with the observer is stationary. All right, for the sake of our discussion, we're going to have the observer stationary. All right, so we're on Earth, and we're watching Victor go by in his spacecraft at like 0.9 C, and he's playing, some Queen. He's playing, 39, because he knows about the story behind it. So he's playing Queen. What are we going to hear? How's it going to affect what we hear, and all that? All right, so we're going to go with the observer is stationary. Now, two things are going to happen here. One, we're going to get the kind of compression or stretch out of the waves that would normally happen due to, regular old Doppler effect. But think about what else is a little bit different. What else do we have to take into account that we didn't have to do when we were just talking about sound of a, police siren as they drive by? What is relativity going to do?
It's going to be a time dilation.
Okay, so we got to worry about time, because there are going to be some time effects now.
And the distance.
And there's also length effects, right? So it turns out that we kind of have to deal with both of those at the same time. All right, so here's what we're going to do. Let's set it up this way. We're going to go with big T here. I'm going to let big T be the time for the period in the stationary frame. Okay, so meaning we on Earth, when we go wavefront, 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 and we're timing that, That's big T, and that's going to be in our reference frame, which is going to be different than the T in Victor's reference frame. So even if nothing else, even if nothing else, the periods aren't going to be the same just because of the time effects, which means if we're talking about a wave like, say, light waves that are always traveling the same speed, that automatically means there's going to be a difference in frequency. Right? So no matter what, there's already going to be a difference in frequency just because of that. Okay, so let's let T be for the period. Big T is going to be the period in the stationary frame. And so in the moving frame, we'll make it T prime. Okay, so this is going to be the period in the moving frame. So I'm going to do the same kind of thing where we use primes for the moving frame. So we'll do the same thing. All right, so far so good. And so let's have it set up this way. So we're going to be observers here. And we're going to have the source moving towards us. Okay, so what I'm going to derive here is just the source moving towards us. We can do something similar for source moving away from us, but let's just derive this one. All right, so let's think about how we get wavelength. Right? The formula for wavelength is the wavelength is equal to the speed times your period. That's one of the ways to get it. Okay, so let's think about what's happening here. As those wave fronts hit us, we're going to say that's a period of t. But what is going to be the effective speed of the waves? Okay, well, if they're moving here at v, we can do the old, well, it's going to be c minus v. Those wave fronts were being produced at a speed of c, but we're going to take away the speed of the source to get c minus v. So this would just be as we see those waves coming in, it's going to appear that they have a speed of c minus v. All right, but let's change this to frequency. So the way we get frequency is to do c over lambda. So this is going to be c over c minus v times t. So this would be the frequency that we on Earth would measure. Now, what I really want to do is I want to compare this to the frequency that Victor would say that these waves are coming out with. Okay, now, Victor and us, we all agree on C. We also all agree on V. He would argue that we're actually coming towards him with a velocity of V. But we can both agree that the relative velocity between us is V. But where we don't agree is with big T, right? Our timing for the period does not actually match his. So let's adjust that. Let's use the conversion so that we can go into his time frame. Okay, so we have that conversion, right? Yes, no, maybe so. That's the one that involves the gamma.
Yeah.
Okay, so here's what we're going to do though. I don't want it with gamma. What I want is actually with the C's and the V's, because I'm going to want to be able to do some algebra on this to kind of simplify it down. So I'm not going to put in the gamma, but I'm going to put it in with the C's and the V's. So what that's going to look like then, we're going to have this frequency is going to equal, I didn't have enough space to finish it over there. So we're going to have C minus V times, okay, now it's going to look weird, but I'll explain where it's all coming from. If you look at that square root doesn't quite look right. Because when we did it, we had gamma was 1 over the square root of 1 minus V squared over C squared. But if I factor out that C squared from the denominator, we get 1 over square root of C squared minus V squared over C, which when you flip that thing over, looks like that. So that's just some behind the scenes algebra that brought us here. It's flipped over because it's actually a gamma times T prime. So I need a 1 over gamma, which flips it over. Anyway, I just wanted you guys to see that it is the same thing. It's just, it looks a little different, but that's only because I did some algebra on it. Okay, but now, good stuff, right? C's cancel. And notice that this guy is a difference of squares. And so it's the square root of C minus V times the square root of C plus V, which means I can reduce those things down. And algebraically, where we are now, we get the square root of C plus V over the square root of C minus V times 1 over T prime. All right, well, 1 over time, 1 over the period, the frequency. So I'm just going to put this into a single fraction or single root. And here's where we're going to stop. Let's go ahead and put a box around this. So here is the Doppler effect due to relativity. So it's actually very similar. If you go back and you look at Doppler effect, it's very similar, but it's just slightly different. And I'm talking about for light, by the way. This was for light waves. It doesn't really apply, like, to be honest, we're not going to care about sound waves when we're going 0.9C. That's so far up and above the speed of sound, right? Like it doesn't really matter, but this is definitely for light waves. Okay, now I just want you to notice, what if, something that's always good to do when you get a formula like this is to go back to the, okay, what if your velocity is 0? Does this become what we would expect, right? If we get out of the relativistic world. Well, if our velocity is V, or sorry, V is 0, okay, we get C over C, which is 1, square root of 1 is 1, and we get F equals F prime. Okay, cool. That matches. That does what it's supposed to do. But also notice what happens as C increases, or as V increases. What's going to happen to this fraction as V gets bigger? And when I say bigger, I mean significantly close to C.
It's going to be undefined, right?
Okay, so if it's equal to C, this is undefined. It would basically say it's an infinite multiplier on the frequency, right? Well, think about that. Does that make sense?
Yeah.
What would happen if we were actually going at the speed of light as we were sending out light waves?
They would just still be traveling the same. Like nothing would change.
And we're basically riding on the wavefront, right? So not we're the observers, but Victor, let's say Victor, again, he's the one that's traveling in a spacecraft. And let's say he's actually going the speed of light. Then that means when he sends out the next wavefront, he's on top of the original wavefront. So all those wavefronts stay together. So what does it look like the wavelength is?
Would it be infinite?
It actually looks like it's zero, right? It would look like there's no wave, basically. There would be one wavefront because the next one comes with the one before it. So thinking about it that way, you go, okay, so it should have zero wavelength. Well, frequency is 1 over wavelength. 1 over 0 is infinite. And that leads to this infinite frequency. So it definitely makes sense that if we are traveling the speed of light, this formula works. Now, let's not travel the speed of light because I don't want to divide by 0. But what's going to happen as our velocity gets bigger? Well, this fraction is also going to get larger. Let's just think about, like, let's say we're going at 0.5 C. Now we're going to get 1.5 over 0.5. So this is going to look like the square root of 3, which is bigger than the square root of 1. If we're going 0.9 C, we get 1.9 over 0.1. So that would look like the square root of 19. Bigger yet. Right? And so on and so forth. And so what's going to happen here is that as that velocity increases, we are going to get a bigger multiplier on that frequency. And that should make sense. Because if Victor is flying towards us, remember that this was all that he was flying towards us. If Victor is flying towards us really fast, it's going to appear like the frequency of these waves is big, that they happen very quickly, right? They're going to be coming bam, 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 bam. All right, so again, this is for light waves, and this is, and I didn't write that over here. So this is the source moving towards the observer. And actually, when I hear the source moving towards observer, it's the same as if we were to say the observer moving towards the source. It's going to be exactly the same effect either way. So if we're sending out signals, so we're sending out light wave from Earth, and Victor is flying towards us, he would actually use the exact same formula to adjust it to what he sees. All right, now, if you do the same derivation, but you go with the source moving away, it turns out that it's almost identical. we just get this guy. I'm not going to bother you with the math because it's, I mean, it's really the same idea, except that one becomes a c plus v, right? Because now the velocity is adding to the distance, basically. So in this case, this is the source / observer moving away from the other. And now if you look at what happens, well, if they're moving away from each other, if we're traveling at the speed of light, this one actually is defined if v is equal to c, but it's going to give us a 0 observed frequency. Yeah, we already kind of talked about that. This just now means we never actually get the waves. Right, the next wave never actually shows up. And so you get kind of the same scenario. All right, now, an interesting consequence of this is thinking about stars, other celestial objects that actually are producing light that we can see. All right, so let's think about, there's some star that's out there making light, and let's say that it's moving away from us. All right, now I'm just going to pick a color because it doesn't really matter, but let's just say that there's a star emitting, we'll go with the kind of the greenish yellow light. Let's not do green. Stars don't really look green. We'll go yellow. Okay, but it's moving away from us. Now, I don't know what frequency yellow light has. I'm actually horrible with frequency numbers when it comes to visible light. I know the wavelengths pretty well in terms of, right, like the reds are in the around 700, the high 6s. The purples are down at like 400. Okay, so like I know those pretty well. But frequencies, I don't really know. But it's just whatever frequency it happens to have. Now, let's think about what frequency we are going to observe. So if it's moving away from us at whatever velocity, we saw that this fraction got bigger. It was bigger than 1. So the square root is bigger than 1. So the frequency we're going to see is a bigger frequency than what's actually being sent out. All right. So in this situation, we will see light of a bigger frequency. Okay, well, if we increase our frequency, that means smaller wavelength. So which way are we going to go on our spectrum from yellow if we have a smaller wavelength? Are we going to go towards the red or towards the blue?
Red. No, blue. It's going to go towards blue.
Yeah, my silence probably made you reconsider, right? Okay, because remember the blues are the lower, the blues and the purples are the lower wavelengths and the reds are the longer wavelengths. So what's going to end up happening, right? So what we end up seeing is light of a bigger frequency or smaller wavelength. And so it will look more green. All right, but better way to think about this when we talk about the smaller wavelength is towards blue. All right, so that's what happens if it's moving away from us. Now, if we change it so that instead of moving away from us, it's moving towards us. So let's just go with the star moves towards us. So now we're going to get smaller frequency. We didn't actually kind of go through the numbers here, but you can probably see as V gets bigger, this number is going to get smaller because the top gets smaller and the bottom gets bigger, and together that drives a smaller number. So we end up seeing a smaller frequency, which means bigger wavelength. And in that case, that means this is towards the red. So what this will look is, it's going to look more orange, because orange is the next color in that direction in the spectrum. All right, so this is the classic blue shift and red shift. I don't know if you've heard those terms. I know that Jacob brought that up last time. I don't remember if it was on the record or not, but he asked about blue shift and red shift. And this is exactly that. You can actually determine which direction a star is moving relative to Earth by looking at the spectrum that it produces and seeing if it's been shifted towards the blue shifted, or towards the red shifted. If it's been shifted towards the blue, that means that it's moving away from us. If it's been shifted towards the red, it's moving towards us. Now, I don't know how much you guys know about spectrum of light and the light that's produced and all that. We'll talk a lot about this later when we get into quantum mechanics and the quantum world. But basically, different elements produce different wavelengths of light when they're excited. And so think about being in a star, there's a lot of energy. So there's lots of excitement and moving around and jumping energy levels. Okay, so like we know what hydrogen produces. You can actually see it in the lab. I wouldn't be surprised if Kathy, I hope she shows this to you at some point, where you can look at gas that's been excited. It starts glowing, and then you can use a filter. It's a diffraction grating that splits the light, and then you can actually see the wavelengths, individual wavelengths are being produced. So anyway, we know what hydrogen should produce. So when we aim this sort of thing at a star and go, oh, that's funny, that's like hydrogen, but it's shifted, we can use that shift to figure out which direction it's moving. And not only do we know that it's moving away or towards us, we can actually determine how fast it's moving away or towards us, because we can use that formula, right? In essence, we know what F prime is just because we know what hydrogen does. We know what F is because that's what we're seeing with our equipment. And we all know what C is. So that means in that formula, the only thing we don't know is V. So we can solve for that and we'll know exactly how fast that's moving. So if you've ever wondered, when they say, oh yeah, this galaxy is moving away from us at such and such a speed, that's how they did it. And I want to say that that was Edwin Hubble was the one who came up with that, or who figured this out. Not 100% sure on that. But that's why we know a lot about the universe in terms of how things are moving. Anyway, But regardless, remember, regardless, there's going to be a change in frequency just because of the change in lengths and time factors. But this is now the Doppler effect. Anyway, so I wore a special shirt for you guys today because this is very appropriate. I know you can't really see it, so let me just bring it down here a little bit. Okay. So it says if this shirt is blue, you're going too fast.
I love it.
Okay, so if I wear this shirt just out and about, I get the weirdest looks. People are like, what the? Okay, so let's think about what's going on there, right? If you're moving really fast and you see me, I'm going by you, right? Even without Doppler effect, whether I'm going towards you or away from you, yeah, there's going to be a shift one way or the other. But in general, think about what's going to happen if you go faster or there's a greater speed difference. We saw that lengths look shorter. So that means that the wavelength of light that's coming off of this shirt, which is in the 600s for sure, is going to appear to you as a shorter wavelength. Okay, well, eventually you could be going fast enough that it's going to look blue. So hence the shirt. But yeah, I don't even try to explain that to people out there. But yeah, this is one of my many science shirts that I really only wear when we're talking relativity. Anyway. Okay, so there's the Doppler effect. Incredibly useful for our knowledge of the universe. But for most of us, that probably doesn't really matter as much as, oh, I don't know, maybe let's talk momentum and energy and all that. So let's turn our attention to those because those are way more useful. Like think back to first quarter calculus. You spent a lot more, well, even not just first quarter. Think about up to this point, how much have you done with Doppler effect versus how much have you done with kinetic energy? Right? No contest, right? So let's actually hit some of these. I was going to say bigger, but how about the broader topics? And let's start with momentum. So I'm going to go ahead and clear this and let's start talking a little bit of momentum. So remember classical momentum? What's the formula to calculate momentum in good old Newtonian world?
Didn't mass and velocity in a specific direction?
Okay, so it is a vector. It's absolutely a vector, so direction matters. And it is just, it's mass times velocity, right? So in good old classical Newtonian world, momentum, P, was m times v, and we usually think of it as a vector. But if we're going to talk about magnitudes, then yeah. Oh, yeah. And Ralph, I just saw in the chat, that's exactly why I'm wearing this shirt, just because it's Relativity Day. I actually had it ready to switch into last time if we had gotten to Doppler effect, but well, we didn't. So anyway, so here's a good old classical mass times velocity. Okay, but we now know that velocities are weird. And velocities, of course, since they're based on distances and times, well, who's actually measuring the distance? Who's measuring the time? All that good stuff. So what we're going to do is let's turn this into relativistic. And here's what we're going to do. We're going to have an object that's moving at some velocity v. This v is going to be allowed to be large. Okay, so large enough that there are time effects and things like that, right? I mean, okay, so let's say that it's moving, at 1/100th the speed of light. We don't care. We can just use good old mass times velocity, right? But eventually we'll get to a point where it's going to matter. Okay, so let's say we've got it moving at relativistic. Now we are going to measure its momentum. So this is going to be the momentum according to the observer. Okay. Now, what we're going to do is we're going to start with just good old how we calculate momentum as mass times velocity. But I'm doing this scalar, by the way, and I'm going to assume that all our calculations are in the direction of motion and all that whenever we do energies and all that, because otherwise, like, lengths don't change and all that. But this momentum, we want to find the momentum according to observer. Okay, but let's just start with the momentum according to the particle. It's going to be its mass times whatever time length. And I'm going to put here delta T naught. So delta T naught, that's going to be proper time. And remember that this particle is what's carrying proper time. All right, now let's change this. So we know how these guys are related. I drew an A and I meant a delta. Right, the T naught is equal to T over gamma. So we can flip that thing over. This gives us a gamma times M times dx dt. Okay, well, dx dt, those are both in our reference frame. And so dx dt is a v. All right, so there's the change. When we actually calculate the momentum of an object that's moving at a speed that's considered relativistic, or basically fast enough for it to matter. And I know that when we first brought this up, you remember Bradley was like, well, when does it start to matter? And I said, well, when it starts to matter, whenever we decide it starts to matter. Well, when it starts to matter, we actually have to use this formula instead. Hey, look at that. We have another multiply by gamma. We haven't seen that at all, he says sarcastically, because everything we've seen so far has a multiply by gamma, right? Times at a multiply by gamma, lengths at a multiply by gamma. Sorry, sometimes it's divide, but if you rearrange it, it's still multiply. So it turns out that the same thing is happening here. All right, so now when it comes time to actually calculating the momentum of, say, an electron, because electrons are moving fast, we're going to have to use this formula. All right, now what I want you to do and what I want you to kind of look at here is how this compares to the classical. All right, so go back up. And I'm going to just draw a graph here that kind of holds these two on there. And this graph is going to have velocity on the horizontal and momentum on the vertical. So this guy, the classical, it's super easy. It's just a line. The slope of that line is the mass of the object. All right, now let's bring back the gamma. Let me actually put that back in terms of the V's and C's and all that good stuff. So gamma is the 1 over the square root. So we're going to have mv over the square root of, well, actually, you know what I'm going to do is the same thing we did before, which was the pull out that c squared and all that. Okay, so that's what this thing is going to look like. All right, now let's look at what the graph of this is going to look like. Sorry, going to look like momentum versus velocity. Okay, so first of all, we got the m times c. Yeah, that doesn't really do anything. That's just constant multiple. But if you think about v as our variable, first thing I want you to notice is that there's a problem here. Right? There are a couple of values, or there's a value for v that's a problem, right? V equals c is bad. What's going to show up at v equals c on the graph?
An asymptote.
Yeah, there's going to be an asymptote here. And if you were to actually kind of look at this thing, what you would see at very small v's, this is going to look exactly the same because gamma is virtually 1. But it's going to get bigger as we go. So early on, it's going to look pretty much like the other one. But then it's going to do this. All right. So the red is the relativistic and the pink is classical. So classical is a bit of an issue because, first of all, you can go past this guy C, but what we actually see experimentally is the amount of momentum increases much faster and actually never reaches C. And this is the first actually really good argument for why you can't travel the speed of light. Because think about what kind of momentum you have to have in order to travel the speed of light. Well, I mean, infinite. And how do you get infinite momentum?
You need pretty much infinite velocity.
Yeah, you'd need infinite velocity, or well, you'd need infinite force or infinite work or infinite energy. Right? So even just looking at this, just momentum itself makes it so that we can't travel at the speed of light. Now, we're going to see more of this for sure. We're going to see some more of this as we talk more about energy and all that. But I want to relate this to Newton's second law. You guys remember Newton's second law? I know because it's like the one we use all the time. But what you may not remember is the alternate form of the second law. Like if I say what's Newton's second law, you're all going to say F equals ma. Right? But there was an alternate form. There was a momentum form. That was force is equal to dp dt. Hopefully you kind of remember that. At least hopefully you remembered enough to go, yeah, I think that's right. And I'm going to believe Bruce at this point in time. But let's think about what's going to happen now if we go to relativity. This is relativistic. Okay, so it's going to be gamma mv. Okay, but I want you to start seeing kind of what the issue is here with this, right? What happens when you accelerate?
Velocity changes.
Okay, so your velocity changes. So we apply a force, you start accelerating, your velocity changes. Now let's say that we're going to, our velocity is changing in a getting bigger kind of way. Okay, if your velocity changes, that changes your gamma. If you change your gamma, that changes your momentum, which, this is so complicated now. And to make things even worse, think about the fact that when we apply forces, say, in the direction of travel versus in other directions, they, like, if they're not in the direction of travel, only the portion that's in the direction of travel has anything to do with relativity in terms of distances, because all the distance stuff, the compression of distance, only happens in the direction of travel. Stuff that's perpendicular to it doesn't matter. This gets really complicated. So now all of a sudden, this thing that we kind of relied on was our go-to for everything becomes a big old pain in the ass. Now, I'm not going to go through these derivations, but I just want to show you the difference, like what you can potentially get. All right, so here's the first one. Let's say, here's the first case that I'm going to talk about. So case one, this is going to be where F and V are in line. All right, so our force is actually in exactly the same direction as our velocity. If you go through the derivation using gamma and V and doing all the integrals and blah, blah, blah. All right.
Real quick, is this
Yeah.
a partial differential equation at this point?
No.
No? Okay.
No, it's not partial. It's just, think about this too, though. The d dt, which t are we talking about? And then how's that related to the other t and the, yeah, okay. Well, anyway, so in case number one, where we're actually in line, it turns out that F is equal to gamma cubed ma. Now, the fact that a gamma shows up doesn't shock you, I'm sure. The fact that a gamma cubed shows up probably does shock you. All right, again, like I said, I'm not going to run through the math. I think the book shows it. If not, you can find it. There's lots of resources where they'll run through that. So let's go to the kind of the other extreme. Case number two is going to be where F and V are orthogonal. So imagine a particle that's going around in a circle, right? Like in uniform circular motion or something like that, where your force is always centrally pointing, and so it's always perpendicular. Okay, well, in this case, F equals gamma ma. Now that one you're probably all on board with, because you're like, well, everything else there was a multiply by gamma, so of course with forces we'll do the same thing. Well, again, that's only if the force and the velocity are actually orthogonal to each other. All right. So what about when we're somewhere in between? What happens when our force is being applied somewhere between parallel and orthogonal? Well, we get some multiple of ma that's between gamma and gamma cubed. How much you get is due to the geometry. What is the angle between them? We're not going to go into that. If any of you end up taking more physics later, like this might only apply to Bradley, I don't know, but there are classes that are only on like relativity, and you spend an entire semester talking about this stuff and you go into great detail and you will learn all about that. That's the one class I wish I had taken as an undergrad that I never did. I never took any kind of like advanced modern physics stuff. In retrospect, I kind of wish I had, because I find it supremely interesting now. That was definitely a case of youth being wasted on the young, if you know what I mean. All right, so the backbone of our physics world is completely shaken now with Newton's second law. All right, well, it is.
I'm
what it is.
curious as to what Einstein observed for him to start thinking like this.
I think what it was I don't know how much it was him observing, but it was things where like you could just see where if all you're trying to calculate are like velocities and you're getting real differences or time differences, and it was sort of consistent, and we always keep running into the same kind of problem. That's my guess, but I don't know. I know that there's some story about how he was like riding on a tram on a trolley and looking at a clock as he was going by it, and that's what gave him the spark. Now I have no idea if that's actually real or not, because you know how we get all these stories, especially about these real important figures in our lives, and we tend to overinflate what they did. So I'm not really sure, but yeah, it was huge, and I don't know if it had to have been Einstein. I think a lot of it was the time. Things were just kind of coming together where there was enough that wasn't making sense that they were starting to find out wasn't making sense, that it was just a matter of time till somebody put it together. But yeah, I tell you, I would have loved to have been around like 120 years ago at those physics tables hanging out with people. Those would have been some wild conversations. All right, so there's Newton's second law. So let's talk energy now. If you're not deflated enough with well, shit, everything is completely different and we're screwed. Yeah, let's go talk energy. Actually, let's clear everything up faster. Okay, so let's think about energy, and specifically, let's just start with the work kinetic energy business. All right, so hopefully you guys remember, we're going to be doing one-dimensional motion, because we're only going to care about moving in the direction, in one direction, make life a little bit easier. But we had that work was, don't want an integral yet. Work was force times displacement, right? And it still needs to be the same thing, right? The first postulate, the laws of physics still have to be the laws of physics. So we're still going to define work the same way. But now if you think about this, okay, so we would do it as an integral, let's say, total work from one position to another. And then this becomes a little dx. Okay. Yay. But now let's think about what's going on with relativity. Force is now no longer force. It's all messed up. The dx, well, that's a length. Lengths are all jacked up. So clearly weird stuff is going to happen. Well, let's see what that weird stuff is. Okay, so let's go to relativistic. So we're still going to integrate, but now that force, well, it's actually going to be a gamma cubed ma, because we're doing one-dimensional motion. So the force is in the direction that we're going. So it's that one extreme that I just showed you. All right, so that's what we're doing. All right, now I want to change this ADX, because basically we have to be really careful about lengths and times and all of that. And so those are the pieces that involve the lengths and the times. Gamma is just going to be what it is from the velocity of our object, and the mass of the object is the mass of the object. If you're concerned about that, because we haven't talked at all about relativity effects on mass, right? We've talked about them with time and with distance. Mass is the other quantity. We don't have to worry about that. If you want, you can just say it's the rest mass. The mass is the mass is the mass. Now, earlier in the development of physics, people started saying that mass got affected as your speed increased. But that's really fallen out of favor, and it's more that we'll say that the momentum is getting affected, but the mass is the mass. The inertial quality of an object is its inertial quality, and that doesn't change. So if you ever read something that says, oh, and your mass is going to decrease as you, okay, that's kind of an older sentiment. We don't really think that anymore. So mass is just mass. We just, anytime we talk about mass, we consider it the rest mass, and then we don't have to worry about it. But the other pieces we definitely have to take into account and talk about, right? So what's going on with these ADXs? So let me do this over here on the side, and let's just look at what A times dx is going to look like. So A times dx, if I replace the acceleration is the change in the velocity in that x direction with respect to time. Okay, well, I can rewrite this as the dvx times dx dt, and dx dt is just vx. So what I can do is I can actually change this integral so that I'm no longer looking at it as an integral in terms of position, but I can look at it as an integral in terms of velocity, because basically what I'm going to do here, if I change this, we're going to get gamma times m times vx times dvx. Now, instead of saying, well, I'm starting at my initial position and I'm ending at wherever, this is going to start at a velocity of 0, and it's going to obtain a velocity of v. All right, so now I do this integral. The gamma and the m are constant. Oh, but they're not. Oh, the gamma isn't constant. So we can't pull that out, right? Okay, well, if you do this integral, and again, I'm not going to bore you with the details. You can actually look at it in the book. It involves integration by parts and all that good stuff, because you got to put that square root of the 1 minus v squared over c squared in, and right. Okay, so this is a pretty gnarly looking integral, but it turns out that it ends up being incredibly simple once you do the calculation. And you get gamma minus 1 times mc squared. All right, so this right here, remember what it was? It was the total work done getting from 0 to V. And if you go back to your work kinetic energy theorem, this is actually the kinetic energy in that particle. So for something moving relatively quickly, the kinetic energy in them is gamma minus 1 times mc squared.
So suppose this particle or whatever it is traveling at the speed of light. Is going to be no work done on it. It's just
Okay, so
zero, right?
so if it was traveling at the speed of light, gamma is infinite. So there would have been an infinite amount of work needed to get it there. Right? Gamma increases as your speed increases. And the limiting value as you go to towards C is infinity. So this is actually the next thing that really suggests traveling at the speed of light is impossible. Or more to the point, increasing your speed to the speed of light. Right? Because this is the amount of work done to get you from 0 to whatever velocity we're talking about. And so if we wanted to get up to the speed of light, even if we weren't at 0, we started somewhere else, realize that if we have infinity and we subtract a certain amount, it's still infinity. All right, so yeah, basically you're never going to get to the speed of light unless we find out that the laws of physics don't work the way that we think they do, which is totally possible, right? I mean, there were hundreds of years where everyone thought, well, Newtonian was the way everything worked. And then relativity came around and went, oh, I guess not. Well, we might get another one of those. I say might, we're gonna. It might happen in my lifetime. Who knows? Like they often like speed up, right? We had to wait a couple hundred years for Einstein stuff. Hopefully we don't have to wait a couple hundred more for the next one. But unless there's some change to our knowledge of the universe, it's not possible to go the speed of light. It just isn't, according to the math. Now, what's kind of nice here is, again, check this against other stuff. Like obviously going the speed of light is an issue, but let's say we're not moving at all, right? If we have no velocity, we should get 0 kinetic energy. Does this formula suggest that?
No.
What's gamma equal when you're stationary? Let's bring back what gamma looks like, right? Gamma is 1 over the square root of 1 minus v squared over c squared.
Just 1.
Okay, so if v is 0, gamma equals 1. Well, 1 minus 1 is 0. We get 0, and we have no kinetic energy. Cool. All right, so it at least matches, because anything that we derive, we want to make sure that it matches non-relativistic, and this definitely applies. And in fact, even if you're going pretty fast, like, you know, a tenth of the speed of light, this difference is still pretty small, right? Like gamma is still pretty small. So it definitely works out. And if you were to actually look at this square root thing and do the power series on it, I don't know if you remember, there's a binomial power series thing, but if you do that and you look at just the first couple terms, this becomes 1/2 mv squared. So it actually does match exactly what it should be for non-relativistic. All right, so you're starting now to see this mc squared popping up. So we're awfully close to that really famous equation. Okay, so here's what Einstein suggested, because he looked at this and he went, you know, this is kind of curious that if you were to kind of break this apart, you get gamma mc squared minus mc squared. And this part right here, this has nothing to do with your velocity. Right? That's just m. That's your mass. Your mass is your mass. And c squared. Okay, well, that's the speed of light. But none of that actually has anything to do with how fast you're going. Whereas the other bit does, right? Because it's got the gamma. So Einstein proposed, okay, then let's just call this thing rest energy, since it has nothing to do with mass, or sorry, speed. And we'll call it E sub r for rest energy. And so he went, okay, so clearly this is energy that just exists in matter because it has absolutely nothing to do with velocity. And if we call this your rest energy, then total energy, that's going to be your rest energy plus your kinetic energy. So that would be mc squared plus gamma minus 1 times mc squared, which is gamma mc squared. So whenever you see that formula, E equals mc squared, first of all, they really should just write E equals gamma mc squared, because that's actually the energy in an object. But E equals mc squared is your rest energy. Now, think about this. If you are at rest, what does gamma equal? I just did it over there, right?
Yeah, 1.
Gamma equals 1. So this becomes E equals mc squared. Holy shit, yeah, that's your rest energy. So there you go. So that's what this whole E equals mc squared is it's just talking about how much energy is in an object just because it exists. All right, so if you have mass, yeah, all of us have mass, but if you have mass, there is energy in your body just because the mass exists. All right, well, this is the foundation of like nuclear energy. We literally destroy matter. We get rid of mass. That mass gets turned into energy, according to this formula. So a big consequence of this is in conservation of energy. Because now when we talk about conservation of energy, it actually has to be mass slash energy, because mass plays a role now. In a closed system, you could actually have an increase in energy but that's because there was a decrease in mass. All right, so this is definitely weird. It's definitely trippy. But yeah, it's there. Now, it's incredible how much energy is in mass. It's astounding. And just to show you, what we're going to do is we're going to find out the rest energy, or calculate the rest energy of a penny. You guys probably have pennies lying around your house. No big deal, right? But let's actually calculate what it is. All right, so we're going to look at the rest energy of a penny. Now, a penny, just so you know, weighs right around 3.1 grams. All right, so it's around 3.1 grams. So if we go and we calculate this, all right, so its mass is 3.1 times 10 to the minus 3 kilograms. And then we're going to take 3 times 10 to the 8 meters per second squared and square it. So you run those numbers and you get right around 2.8 times 10 to the 14th joules.
That's ridiculous.
Yeah, I'm trying to think. Is that tera? Is 10 to the 12th tera? Because 10 to the 9th is mega. No, 10 to the 6th is mega, 10 to the 9th is giga. So I think this is 280 terajoules, which I mean, I can't even imagine that number. Right? Think about how much water we could heat up with that.
The entire planet.
You remember the specific heat of water, right?
It's like 3.18 joules.
Something like that. I think for 1 gram or something like that. Yeah. So it's like nothing. It's incredible. And this is just 1 penny. That's just a penny. Think about the rest energy of the material that makes up your body. And no, I'm not saying you're fat, any one of you, because it doesn't matter. I mean, take a baby. I mean, I just imagine 1 kilogram. A kilogram is going to be on the order of 1,000 times as big. So 10 to the 17th. Holy crap. Right. So we get incredibly large amounts of energy stored up in mass. But that's why nuclear energy can produce so much. Because any one of those reactions releases just a small amount of mass, but it ends up being a large amount of energy. And we'll definitely talk more about that when we get to, atomic structure and all that later in this course. But yeah, that's coming. All right. This is the other reason, like, in Star Trek, I know it was just Star Wars Day, but we'll go to Star Trek. You know how their engines are matter, antimatter engines, and that's kind of the idea. The idea, the science behind that, which is legit, is if you take material and have it meet its anti-material, so like an electron meeting a positron, those two things will obliterate each other. And so all of that mass gets destroyed, which according to this formula gets all turned into energy and then Starship Enterprise is powered. So that's a real thing too. Antimatter and using antimatter.
What's the difference between mass and matter exactly? Is it how much matter there is?
Okay, so mass is a specific measurement that is looking at your resistance to motion, right? It's a measure of your inertia. And I think when we talk about matter, we're just saying that it's stuff that has mass. You know what I mean? So it's not like, it's not a specific number, it's not a specific measurement. So when we say, all right, this is matter, it's made up of stuff that has mass. Whereas the mass of it is how resistant it is to motion, this collection of matter. Does that make sense? Matter is more just a qualifier word,
Yeah, that makes
where
sense.
mass is an actual quantity. All right, so now we've got rest energy. Now you know where E equals mc squared comes from. And it wasn't just Einstein had a bender one night and came up with something crazy. It's based on reality. Okay, now I want to show you one other kind of interesting relationship that we can get between energy and momentum and all that. And this really comes just from doing some algebra and playing around with this. And again, I'm not going to bore you with the algebra. If you want to see it, you can find it. Okay. But if you just start with E squared, so this guy right here, gamma mc squared, square it. And you kind of move things around and you fiddle around with it and all this. You get kind of a Pythagorean theorem looking thing. Good old like a squared plus b squared equals c squared deal. But this is what we get. All right, now I kind of want to break this down for you a little bit and look at this individual pieces. So looking at this guy, mc squared, you all recognize that. And that's the rest energy. This other piece that has the P, so P is momentum. And so while it's not just momentum, it's a momentum type thing. Right? It depends on your momentum. All right. So this is just another way that we can kind of break this down. But this has some like major consequences. Again, this topic, we could talk forever just on this equation, but I want to share with you kind of the biggest, most important consequence of this. All right. And it's this right here. Suppose you have no mass. Okay. So you've got no mass whatsoever. So that means you got no rest energy. So that little bit goes away. So this means that your energy is going to equal the product of your momentum and the speed of light. Okay, so if you're massless, this means you still have momentum. So that's the first thing I want you to realize. I put an exclamation behind that because that's crazy shit right there. How can you have momentum if you don't have mass?
I have an idea.
We define momentum as mass times velocity. I mean, even when we went, relativistic, it was still gamma times mass times velocity. But if mass is 0, that's 0. Okay, so Bradley, you just said you have an idea. What's your idea?
Just the universe itself moving.
Well, I guess if we were going to say relative to something else and we were looking at it, but I'm just saying, like, even in my little reference frame right here, if there's something massless, it still has momentum. Okay, don't worry. We'll see why this has to be, but it's true. It works. Okay, so you're going to have momentum. The other thing that we're going to see has to end up happening is that it travels at C. So if you've got something massless, it has to be traveling at the speed of light. Okay, I don't know about you, but my brain's starting to hurt. Okay, well, let me show you why. Let me show you why both of these work and why they must be. Now, the first one I'm going to do is kind of the second one. And I know you're not going to be terribly thrilled with how I do this, but I'm going to do it this way. Let's think about the formula for energy and momentum, and let's put them together here in this formula. Okay. So if we've got E equals PC, you saw that E is equal to gamma mc squared. Okay, momentum we saw was equal to gamma mv. So we get gamma mv times c. So gammas cancel, m's cancel, and we're left with c squared equals v times c, which tells us v equals c. All right, so there you go. The formulas say that v has to equal c.
So is this basically saying that light is energy?
It's saying that light is massless.
Okay.
And
that
yet
too.
still has momentum.
Okay, yeah, that's weird.
That is definitely weird. Okay, so this travels at v equals c. Now, when I said I'm going to do it this way, and some of you are not going to like it, do you get what I'm talking about there? What I meant by that? Think about this. I just slashed those m's. But what does m equal?
0.
It's 0 because we're talking massless. So you might go, okay, well, you can't do that. Okay, well, what I'm really slashing is gamma and m together. And you'll see why we can actually do that. But anyway, so just from that little bit of algebra, you're like, okay. But let's go back to this. Okay, but wait a minute. How can I have momentum if there is no mass? Okay, so come back to momentum. We have that momentum is gamma mv. And we're saying that in essence, m equals 0. But we just saw that we kind of need to be traveling at the speed of light. What does that make gamma equal? If you're going the speed of light, what does gamma equal?
It's also undefined.
Okay, it's undefined, but in essence, it's infinite, right? Because it just keeps going up and up and up and up. So it basically becomes infinity. So let's think about gamma times m. So infinity times 0. What do you get when you take infinity times 0?
Infinity?
Not infinity. I
Zero?
mean, it could be infinity. It could be 0. It could be 37. This is one of those indeterminate forms. Remember when you did L'Hopital's rule? 0 over 0, infinity over infinity. Well, infinity times 0 is yet another one of them. And so in order to get momentum, to have a non-zero result here, because it can't be 0, like we know it has to have momentum. That means that gamma has to be infinity, which means we have to be traveling at the speed of light. So this is really the argument for why something massless has to be traveling at the speed of light, is the fact that it has momentum, even though that feels terribly wrong. Okay, so something that's massless, light, has to travel at the speed of light, but still carries with it momentum.
Would another thing like that be gravitational waves?
Gravitational waves travel
Yeah.
at the speed of light. They have no mass. They do have momentum. Yep. Okay, now check this out. If you have some mass, okay, so you're not massless anymore. You have some mass, and it can be the smallest mass you can imagine. All right, well, now what happens is you cannot have infinite gamma. You cannot be traveling at V equals C. So this also is another argument for why you cannot travel the speed of light. You cannot, I cannot, because we have mass. All right, so this whole thing about light having momentum, even though it doesn't have mass, we will talk more about. It is a real thing. Have you guys ever heard of solar sails? So a solar sail is an idea for like interstellar travel, or like, traveling out in space, where it's exactly what it sounds like. You have a big sail, like on a sailboat, but what it does is it harvests the momentum from the light being produced by the stars, because they definitely have momentum. Kathy has this cool little thing. You may ask her about it. Maybe ask her about it tomorrow. What it looks like. It looks like an old flashlight, or not light bulb, an old style light bulb, and in it there's like a little It's got like 4 little diamond-shaped paddles that are all connected, kind of like on a pinwheel. And one side of them is painted black and the other side is painted white. See if she'll crack that out and shine a flashlight on it. That's all I'm going to tell you about it. I want you to see what happens, but ask her about that. Just say, hey, do you have the little like black and white pinwheel thing that you shine a light on? She'll know what I'm talking about. And see if she can show you that, because that will convince you that light does have momentum. So anyway, so relativity jacks everything up. Everything that you know about physics. You have to go, yeah, but what if the speed is fast? Because if we're just in, oh man, I stopped my video all that time ago. So you've just been looking at me drinking beer the whole time. Anyway, so if you are at slow speeds, everything you know is fine. Everything we've taught you in physics so far is totally cool, totally works, not a problem. But as soon as we start getting to high velocities, like 1/10 of the speed of light or more, everything gets jacked up. Or if our precision is so good that we can tell the difference, we do have to worry about it at slower speeds. But a lot of the things that we investigate in physics now travel at those speeds. Electrons travel at those kind of speeds. These subatomic particles, like if you look at a linear accelerator, right, or a particle accelerator like at CERN or Stanford, Fermilab, I mean, they get those particles up to insane speeds, so then they can smash and produce new particles and new weird things. Relativity matters a lot in those cases. All right. So for some of you who the only reason you're taking this physics is because it's for engineering and you're going to be designing bridges. Okay. Nope. This will not affect anything you do. But there are definitely places, like if you're thinking about becoming an astrophysicist, an aeronautical engineer, this stuff's going to matter, right? But it's cool as shit, right? It is super cool anyway. So it's worth talking about. All right. Well, I think I'm going to stop here. This is a really good natural breaking point. Going to let you go a little bit early. Yeah, we're right on schedule. Everything's cruising well. So just to remind you guys, chapter 5 homework, the relativity homework, is due on Tuesday. The first exam is going to be on Thursday, a week from today, and it's going to go through chapter 5. So it's going to be optics and relativity. We'll talk more about it on Tuesday, but I want to make sure you guys know so you can start studying and planning on it. So it'll be all the optics and then relativity. I will get all the homeworks graded. I will look at all those and grade them for sure this weekend, just so that you can see my comments if there are any big issues that you're running into. But as always, feel free to reach out to me if you have any questions on anything. All right. So I think that's everything I have for you guys. Any questions you guys have for on the record?
Yeah, what does relativity do to affect our equations for like thermodynamics?
So thermodynamics, not much actually, because the only thing that it can affect would be like conductivity. Anything that has time dependence or distance dependence, those can get affected. So basically what that would mean is if we were looking at how quickly heat transfers, let's say, through copper, you and I, like if you're moving at high speed, you and I wouldn't agree with how long it takes for the heat to move through. But they would still be consistent, that if I were to take my amount of time and look at the length of the copper wire according to my lengths, it would still, like, everything would still be consistent. It's just we wouldn't agree with those numbers. So it will change things like that. Temperature, it doesn't affect, because temperature is just a measure of how much energy is in the object, right? And the amount of energy in the object, well, I guess maybe it would change how we would read temperature, because I would say that you have more energy in you because you're at a higher gamma. That's a good question. No one's ever asked me that. I do know things like in E&M, what's crazy is like an electric field becomes a magnetic field, or vice versa. Right? Like, think about the difference between an electric field and a magnetic field. For one of them, you have to have motion, and the other one you don't. And so now all of a sudden, well, it's stationary according to me, but it's moving according to you. You know, so you get some weird things like that. But thermodynamics, yeah, you know what? Let me think on that a bit. Because now I'm starting to think maybe we would record different temperatures. I don't like that, but that might be true.
I'm sorry. I just,
No, it's all good. No, I love the questions, and obviously I don't have all the answers, right? And I love when you guys do this, because it makes me think. It makes me, you know, and you heard me, like, I started going, and I was like, whoa, wait a minute, because part of my brain went to nah, but now there's this consequence. So no, I appreciate it, Bradley. But yeah, I'm not sure. That's cool. I've been teaching modern physics for a long time, and that's the first time that's ever been asked. That's impressive. All right. Okay. Well, I'm going to go ahead and then call it for the day. So have a great weekend, and I will see everybody on Tuesday.